Welcome. It's hashtag Webinar Wednesday. Hashtag Webinar Wednesday. I'm Doug Sesserman, privileged to serve as the Chief Executive Officer of Americans for Ben-Gurion University, and welcome to Webinar Wednesday. Today we have Dr. Oren Shriki, who runs BGU's Department of Cognitive and Brain Science and is a heck of an electric guitar player, also on the faculty band, among other things. This is just going to be terrific. Thank you all for joining us. We had really great RSVPs for this webinar, over 200 people and growing. So thank you for attending. For those of you who have joined us before, we really appreciate it. For those of you who are joining for the first time, thank you. The deal with these webinars is that if you give us a half an hour, in this case, we'll give you a glimpse into one of the most vital institutions to the future of Israel, Ben-Gurion University of the Negev. And today we're going to be talking about brain science. If you just don't get enough after this program, we have more great programs coming up. In fact, the president of Ben-Gurion University, Professor Daniel Shamovitz, is coming to Colorado, my home state. He'll be doing events in Aspen and in Vail. In middle of August, we have another webinar with Professor Naama Atzaba-Poria. She runs our reflective parenting program, a wonderful person that does incredible research on how to help people be better parents. And in October, on October the 3rd, we're having our first hybrid meeting where we'll be having an in-person and streaming live on the internet symposium on BGU's new School of Sustainability and Climate Change. So please join us for any or all of those. And if you want more information, just always go to our website, www.americansforbgu.org. Okay, I want to thank the behind the scenes excellence of the team, Melody Makhtarian, Kara Bortman, Liz Kirshner, and Sari Berkovich, our marketing department. We are live on Facebook and we can't do anything without these great people behind the scenes. Oren, are you ready?
Yes.
All right, this is going to be perfect. So remember, if you have a question, just click on the Q&A function. I'll read those questions throughout the program and we'll feed them to Oren. At the last part of the program, the last 10 minutes, we'll just open it up to Q&A. Oren's put together a really nice presentation on his fascinating work. So let's get going. Let me introduce Dr. Oren Shriki. He completed his undergraduate studies in physics and doctoral studies in computational neuroscience at the Hebrew University in Jerusalem. He then became a high school teacher, which I see that a lot of that job in you, Oren. It's great. For several years, he taught physics, as well as courses in computational neuroscience. Upon completion of his postdoctoral work at the National Institute of Mental Health in Bethesda, Maryland, he established the Computational Psychiatry Lab at BGU. And in 2018, Dr. Shriki established the Neurotech student community at BGU, which is now a nationwide community. During last year, he founded NeuroHelp, a startup company which develops a novel wearable device that can predict epileptic seizures. Dr. Shriki currently serves as the head of the Department of Cognitive and Brain Science at Ben-Gurion University and is the leader of what we call BGU's Neuro Tech Hub. Welcome, Oren.
Thank you very much, Doug, for the warm introduction. Thank you for these words. So today I will present some of the research in my group and the vision that I'm trying to promote here at BGU. In recent years, there's a growing interest in the field of neurotechnology. Advances in understanding brain dynamics in congruence with novel hardware for measuring brain activity allows us to develop wearable systems that can monitor brain activity in real time and apply it to a wide range of uses, from brain-computer interfaces that can assist people who are unable to control their muscles to helping healthy people maintain their Neurowellness. By the way, some of my students asked me, why did I choose this image? So it's a brain that lifts weights. So this symbolized for me fitness, brain fitness or Neurowellness. Perhaps I should have said that they used to be my students. Here at BGU, we have all the ingredients to become leaders in this field of neurotechnology. To some extent, we already are. The goal of the Neurotech Hub, which I will describe later in this talk, is to serve as a space for students to develop and test ideas in neurotechnology and take them all the way to a working prototype and even establishing relevant startup companies. But let me start by illustrating the need for such technologies through a touching story. This publicly available video we see here shows a girl named Oren during an epileptic seizure. This is a state of enhanced and synchronized neural activity which can lead to unintentional movements and even to loss of consciousness. Oren suffers from frequent, unpredictable seizures since she was 2.5 years old. Despite many treatment attempts and hospitalizations, there is no medication that can help her. And she must wear a helmet for safety reasons. Cases like the one of Oren and others who suffer from unpredictable seizures provide a strong motivation for our research. To gain insight into epilepsy and into other disorders, we use, among other things, tools and concepts from physics. I'll try to illustrate. So, my background is indeed in physics, and I have special interest in the study of systems that transition between different states of matter, like water between solid and liquid. You all know about that. Now, near the transition temperature, special phenomena take place. And it turns out that there is a deep analogy between physical systems near the transition point and the dynamics of the brain. I'm talking about systems in physics, physical systems that can transition between different phases, like water between solid and liquid. And there is a deep analogy between such systems and the brain. We hypothesize that brains organize to operate not far from such a transition between different phases of brain dynamics. Such a critical state has computational advantages for information processing. However, deviations from the right operating point can manifest in different disorders. In what we call a subcritical state, the interactions among neurons are too weak, and activity dies out prematurely. This could manifest in disorders of consciousness, like a vegetative state. In a supercritical state, the interactions among neurons are too strong, leading to epileptic seizures or to hallucinations, namely percepts without external stimulation. You can think of the subcritical phase as analogous to a liquid phase, and of the supercritical state as analogous to a solid phase. It is optimal to be in between. It's all about the balance. Another useful analogy is to the rate of infection of the coronavirus, which is measured by the reproduction number R. We all know about the R these days. So R is the number of people that one infected person will pass on a virus to, on average. Similarly, we can estimate the R of the brain, namely, if a single neuron is activated, how many neurons will it activate down the road? A subcritical state, on the left side, corresponds to R smaller than 1, where activity dies out too early, whereas a supercritical state corresponds to R larger than 1, where activity may blow up exponentially, leading to a seizure. So that's some of the basic science that we are trying to do. And the basic idea is that mathematical concepts from physics are very useful for analyzing such critical systems like the brain. And they provide new insights about brain dynamics. Indeed, we found that measures from the field of critical dynamics, when applied to brain activity data, can serve as sensitive biomarkers for a wide range of neurological and neuropsychiatric disorders. For example, they are sensitive to differences between patients with schizophrenia and control subjects. They are also sensitive to mild cognitive impairment, a precursor of Alzheimer's disease. Thus, we might use that for early diagnosis of Alzheimer's. So what do we do in practice, you may ask? In practice, our main focus is on EEG activity, electroencephalography, which is often called brainwaves. So we record this kind of brain activity and analyze it. The technology involves electrodes that record electrical activity of the brain at a high temporal resolution. And for example, it is well known that activity in different frequency bands, denoted by Greek letters like alpha, beta, gamma, reflects different aspects of cognitive function, like drowsiness or concentration. We extract from the EEG these metrics, as well as more advanced metrics like the ones based on critical brain dynamics. which provide additional valuable information. And we analyze them to identify all kinds of biomarkers and diagnostic tools. Now, conventional EEG systems look like this, and they involve the use of conducting gel. One has to inject it, and it creates good contact between the scalp and the electrode, but it's really cumbersome. Luckily, in recent years, we see more and more modern systems that are wearable, wireless devices with dry electrodes that can penetrate the hair. They do not require any conducting gel, and they allow us to do essentially neurotechnologies for everyone. So, for example, you can have this system that it's essentially earbuds, but it has EEG electrodes, and no one knows that this is essentially an EEG device. So these kind of devices allow us to go from the lab to real life, essentially. Now, to illustrate how we go from basic science to neurotechnology, I will describe our work in the context of epilepsy. We analyzed a large clinical database of EEG data from more than 160 patients with epilepsy. We analyzed it using measures of critical brain dynamics as well as additional advanced measures. And we obtained very promising results. After obtaining these results, we wondered whether this could have practical applications. And we started asking questions like, can we predict seizures? Can we do that non-invasively using scalp EEG? How early? We found out that we can go even to 1 hour in advance, and we see some kind of signs in the EEG that there's going to be a seizure in about an hour. How many electrodes? This is important for the exterior subtlety of the device. If you want people to actually wear it, it cannot have 20 electrodes. So we were able to show that we can use as few as maybe 5, 6 electrodes. And also considerations of computational power. If our algorithms have to run on a smartphone app, that's also important. So we asked all these questions, and then we were able to obtain a research grant from the Israel Innovation Authority that helps us study these practical aspects. The encouraging results motivated me to establish a startup company called NeuroHelp. And I was very lucky to find amazing co-founders to join me on the journey. During the previous summer, we participated in the Oasis Startup Accelerator of BGU's Entrepreneurship Center, Yazamut 360. The tools we learned there helped the company become more mature, and not long after the accelerator, we managed to raise funding. Today, we have offices at the high-tech park near the university, and we are moving forward on several fronts. By the way,
for those joining us for the first time, BGU is once again recognized as one of the top universities in the world for entrepreneurship. That entrepreneurship comes from ideas that might emanate from the faculty, in this case, Oren's terrific work, and also from students. Yazamut 360 is a program. Yazamut means entrepreneurship in Hebrew, that has a variety of different programs to encourage that entrepreneurship. Oasis is this accelerator program, and my understanding, Oren, is that you won the competition.
So the Oasis was not a competition. You have to be selected to get there. We was like 6 companies out of 12 that were selected, and the Oasis was essentially a course, a 3-month course. Every Tuesday, we had a full day from morning to afternoon of lectures and activities by mentors, and we learned concepts from how to formulate a company vision, how to identify the different kinds of personas of customers that can use the device, the product, to think creatively about the product, to develop the minimal viable product, MVP, to identify or define KPIs, key performance indicators, business plan, financials, etc. So it was great. I think for us scientists, the idea is to develop common language with the business people.
And in essence, this is applied science or transformative science at its best. You're taking work that you're doing in the laboratory, and you have now turned that into a wearable device that enables epilepsy patients to know that a seizure is coming and get to a safe space.
That's right. In a moment I'll describe.
Okay.
So
Right.
by the way, last summer, indeed, the company won first place in the Silicon Egg startup competition. And just yesterday, we were informed that we are one of 5 winners in another competition among e-health startup company. So what's the problem that we're trying to solve?
Okay, so it was my mistake. Oasis was the accelerator that helped you think through the ideas, and then you went and won a couple of competitions.
That's correct.
This is amazing.
Patients with epilepsy have a very clear need. They suffer from poor quality of life due to the unpredictable nature of seizures. Furthermore, their safety is compromised, limiting their ability to enjoy common activities such as biking or swimming. They just don't know when the next seizure is going to happen. Just a story about a year and a half ago here in Israel, a young lady was standing near the light train railway in Jerusalem, and she had a seizure and she fell on the tracks and lost her life. Now, epilepsy, it's about 1% of the world population, around 65 million patients around the world. And about 30% of them, 20 million patients, are treatment resistant. They do not respond to medications, so they're not balanced. They don't know when the next seizure is going to happen. So what's our solution? We call it Epiness. And the basic idea is that we have algorithms together, some kind of hardware, a portable hardware, like you see here in this image. It should be a very subtle EEG system. We are designing it. These are not the systems that you see here. And we have developed algorithms that pre-process the data. Essentially, they remove artifacts and noise. They extract some informative measures about the brain signals. And then we feed them into machine learning, artificial intelligence algorithms that are trained on a large database to predict the seizure, to tell us whether this piece of brain activity comes from 1 hour before the seizure or from a period which is remote from a seizure. And we found that we have very high precision. So we have essentially 2 algorithms, one for detecting a seizure as it's happening, and another for predicting it. And we were able to predict it 1 hour in advance, which is really cool, taking into account that we are using non-invasive technology.
How unique is this, Oren? Does anything else exist like this, to your knowledge, in the world right now?
So there are some devices which are invasive, but you do not predict seizures. They just measure in the brain, and it's very hard to install them. It requires a surgery, and it's very expensive. There are other creative solutions. Maybe you know about some kind of dogs that can tell in advance that there's going to be a seizure, but they also cost like $20,000, and you have to go with them to the mall. So what we want to do is this kind of wearable, non-invasive system, which will be really hidden and sleek. So this is unique. And we know about other solutions, but only in the context of detection, not of prediction. And prediction is what's really important for the safety. Because if you already have the seizure, it might be too late. So now, there are many interesting projects going on in the lab. I mentioned one of them, this seizure prediction. And today, in the interest of time, I'll mention only a handful. So another cool project is this project where we develop a pilot helmet embedded with EEG sensors, which is planned to monitor the pilot's brain. Now, the trigger to this project was the tragic death of Asaf Ramon, the son of Ilan Ramon, the first Israeli astronaut. During a training dogfight, a fight between airplanes, he performed a sharp maneuver. And as a consequence of the blood draining from his brain, because of the acceleration, he lost his consciousness and crashed. While I was at the NIH in Bethesda, Maryland, I was contacted by the representative of the Israeli Air Force. And he asked me whether, the representative in Washington, D.C., and he asked me whether we could develop a technology for preventing this so-called G-lock, or G-induced loss of consciousness. And I thought that, yes, we might be able to do that with EEG. And if we're already embedding EEG in a pilot helmet, why not go for other things as well and monitor the brain in the larger sense? So when I came back to Israel, we started the collaboration with the Israeli Air Force, and we are working on this loss of consciousness, on spatial disorientation, fatigue and drowsiness, high cognitive workload. For example, this accident was caused by high workload on the pilots. It's kind of interesting, but in modern cockpits, there are instruments that monitor everything on the plane, except for one device, which is somewhat important for flying the plane, this one. And the helmet that we develop may lead to a new instrument that would be there and would generate alerts regarding the pilot's brain. If there is an alert, for example, for spatial disorientation or for an upcoming loss of consciousness. So we actually work with pilots, and these are very unique experimental setups. For example, here you see a fighter pilot cadet with the EEG cap on his head in the centrifuge capsule, and it's in the Netherlands, and he has to avoid losing consciousness, even at acceleration as high as 9 Gs, which means that his weight becomes 9 times greater than his normal weight. So yeah, we hope that we will be able to complete this and deliver this kind of pilot helmet with EEG. It's a cool project, but for us, the sky is not the limit. There are relevant challenges in space too. For example, a manned mission to Mars and back may take more than 2 years. So it's a long time. And microgravity affects the body and the brain in multiple ways. And a major open question is, how do long-term space missions affect the brain? We don't know that. Luckily, Eitan Stiebe, a former fighter pilot and a good friend of BGU, by the way, will travel to the International Space Station next year, and he will stay there for 8 days, around the first quarter of 2022. What we plan to do is to measure his brain activity from day to day, before the mission, during the mission, and after the mission, twice a day, and follow the daily changes, how it changes from Earth to space and during the stay in space. And for this, we joined forces with EEG Sense. It's a startup company in Israel that develops a high-quality EEG helmet. It's very unique. It has some mechanics inside it that adapts the sensors to the subject's head. And we hope that this project will demonstrate the feasibility of monitoring astronauts' brain activity and helping them maintain their neurowellness during the long space travel. Over the past few years, I realized that students are highly motivated to work on neurotechnologies. It's really amazing. Their eyes start to shine when they start talking and working on neurotechnologies. So in 2018, I established the Brainstorm Neuro Tech community here at BGU, together with some of my students. Amazing, they did an amazing job organizing all this. And we started it by organizing monthly talks, workshops, and other events. In March 2019, we held the first Ben-Gurion hackathon. You see here the image Ben-Gurion hackathon, and it attracted students from all over Israel. It was a great success. And as a consequence, students in other institutes wanted also to have brain tech communities. And this led to the establishment of local chapters, essentially in all academic institutes in Israel. Now it's a nationwide community with more than 500 active members. They have many events on a weekly basis. And it's amazing. It helps the student network and interact with the neurotech industry. One of the initiatives from this community was that we established the Neuro Tech Hub. Here you see it. It's a space for students to work, and essentially the vision behind the hub is to allow them to develop neurotechnologies using all kinds of equipment, like wearable EEG systems, all kinds of sensors, robotic devices. You can see them here, some robotic arms that we managed to obtain, virtual reality, drones, 3D printers, laser cutters, you name it. That's the vision. That's what we want to have there. And we started. And students work on the projects in interdisciplinary teams, students from cognitive and brain sciences collaborate with students from engineering and computer science, and they try to make a proof of concept of a certain device, and maybe one day some new startup companies will emerge from this. So we've already been holding workshops and events there. hackathons, and one of our plans is to have an international summer course on neurotechnology. So the student in the course will hear lectures from experts, but they will also work on hands-on projects. The plan is to have it next summer. And we do all this in collaboration with the Azamut 360 Entrepreneurship Center.
The coursework in the hub today and in your classes is all in Ivrit or in English?
Yes, yeah, I mean, I could teach in English, but currently it takes place in Hebrew. And this is a course that took place this year. It's a new course that we established here at BGU, and it's very unique. We call it BCI for ALS, Brain-Computer Interfaces for Patients with ALS. People with ALS gradually lose their ability to control their muscles and communicate. And the idea of this course was that it's a year-long course. Students learn about EEG, brain-computer interfaces, machine learning, but they also gather hands-on experience, and they learn about entrepreneurship and product management. But the important thing is that during the second semester, they actually work with ALS patients, which we call mentors. So each team of students was teamed with an ALS mentor, and the teams, they work to identify the needs of the mentors, and then they customize brain-computer interfaces to their needs. It's really moving. I mean, you see some of the pictures of our students working with some of the patients. This guy on the right, another on the left, they all allowed us, they signed a certain form that we could use it publicly. And we also collaborated with other universities, with Haifa University and the Technion, and it was a great success. Next year, even more institutes will join us, and it's a really unique national course where we're trying to help those patients communicate.
And Oren, just going back to a second on the Neuro Tech Hub, are you aware of any other institution that has anything like this?
I think we are the first, but I know that at the Hebrew University, they have some funding for that, and they are going to establish a hub too, following us.
But the idea, it's multidisciplinary, correct?
Yes.
The students, you have first degree, graduate degree, different disciplines all coming together to try to solve.
Yeah, we like all of them, undergrad, graduate, all of them can contribute. If you're a maker, so to speak, if you like working with 3D printers and small computers and these kind of things, or if you know how to program apps, if you know how to control drones, whatever your skill is, of course, if you understand a thing or two in brain sciences, it's good. Come work here. It's going to be fun. And so I'd like just to wrap up and get back to the vision I presented earlier. I believe that you will see that over the next few years, neurotechnologies will pop up everywhere, from brain-computer interfaces for people with disabilities to seizure prediction devices, early diagnosis of Alzheimer's and other disorders, but also to education, helping students, assessing, for example, cognitive workload of students in workplaces, essentially Neurowellness for everyone. And our goal is to harness the cutting-edge brain research, which takes place here at BGU, and transform people's lives. We believe that this will have a substantial social impact. And as I mentioned before, BGU has all the necessary components in one place. We have a strong brain sciences community, the Faculty of Engineering, the Soroka Medical Center across the street, the Azamut 360 Center, and more. So with that, I'd like to finish. Of course, nothing of this would have been possible without the hard work of the incredible students in my lab. I feel very lucky to work every day with such a wonderful interdisciplinary group of students. And that's it. Thank you for listening. And I'll be happy to take questions. And if someone wants a more prolonged discussion on some of the things here, I would be really happy to have additional sessions.
Thank you very much, Oren. That was great. We're getting a lot of questions. One just came in from Bert Foer. He's asking, when an invention like you're describing of yours is commercialized, is it owned by the university, yourself as a researcher, or some combination?
It's a good question. It's a combination. It's kind of interesting. The university used to have a certain agreement where it shares 50-50 with the equity is shared 50-50 with the researcher. So for example, if some investor gets 30% in the company, the 70% are divided 35-35 between the researcher and the university. But for the companies in Oasis, they wanted to help things to really move forward. So they changed it a bit in favor of the researcher, which I think is really nice. And I think it was really helpful for us. And it helps us to raise funding.
Yeah,
But yeah, the university, if we succeed, the university is going to see that too.
Yeah, for those unfamiliar, we have what's called BG, which is the tech transfer company of the university, and it helps with commercializing these ideas from the laboratory to an actual startup company and eventually to industry. We're really proud of the work that you're doing, Oren. It's amazing. My wife Sue, who you've met before, I know you know she has epilepsy, and so she wanted me to ask you a question about the size of a wearable device. What's the path to make something that people would actually wear all the time?
That's a great question. I think this is going to be one of the toughest parts of our work. We want the device to be as hidden as possible. It has to be accepted by the community of patients with epilepsy. So ideally, we would like it to be hidden inside a baseball cap or other fashion kind of gadgets. So we think there will be different versions of the device, perhaps, in terms of the design for kids and adults, for ladies and men, because it has to be hidden. So we are thinking about relatively few, as I said, below 6 sensors. And it could be like a headband, but very thin, very light.
We've got two questions, and then we're going to close because we've already used our 30 minutes. David Mogul's asking, do you have any current collaborations with any US faculties, universities in the States?
We're trying to. I just got a rejection on a grant which I submitted with a guy from UCSD, University of California, San Diego. I'm always in touch with some people in the US, and I visit, before the corona, I used to visit a lot. Currently, I don't have an active collaboration with someone in the US, but
I know you're coming out to the West Coast, right, in October
yeah.
to go to UC Irvine, and then we're going to have you traveling to other parts of the country.
Yeah.
Okay, Daisy Henderson is asking, with the recent advancements and emergence of OPM, optically pumped magnetometers, if I said that right, MEG technology, have you explored using MEG or other types of signal sensors in your research? And are there any advantages over EEG?
Yeah, this is really cool. Now, I used to work with MEG, magnetoencephalography, which is like electroencephalography, but measuring the magnetic fields rather than the electric fields. Now, it sounds very similar, but it's really quite different. So MEG devices are really the common devices, not the OPM, which we'll get to in a moment. It's really expensive. It's like a few $1 million. Just the shielded room is like $1 million. But I used to work with this technology at the NIH in Bethesda, Maryland. And it gives very high quality signals that you cannot get with EEG. The EEG signals are really affected by the, what we call some kind of things that wrap the brain, some membranes that wrap the brain and the scalp. So it's really distorted, the EEG signal. Whereas the MEG, it just goes throughout the brain easily and it's not distorted, so it's kind of better. So there are many advantages to, so the OPM is a technology that it's kind of a wearable MEG system. I wish I had one, yeah, we could do cool stuff with it. But it's really very recent. Like, it just, yeah, we just have it now on the market, I think.
All right, thank you very much on that, Oren. Okay, our half an hour is up. We held on to the audience, so your science was terrific, and the audience stayed and participated. I just want to close with a quote from David Ben-Gurion, the founder and first prime minister of Israel, and the guy whose name is on the door of our university. He once said that dreams are capable of transforming the natural order by the power of vision, science, and pioneering capacity. And you, Dr. Oren Shriki, represent all of those in one amazing human being. We're proud of the work that you're doing at Ben-Gurion University to advance Israel and to improve lives all over the world. Thank you for being here. Thank you all for attending. Stay safe and healthy.